Okay, chapter 4 is all about radical and rational equations and polynomials and things like that. I'm going to combine 4.1 and 4.2, which is polynomials and graphing techniques. So a polynomial function of degree n, where n is a whole number, is a function of the form f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 times x to the n minus 2 plus etc. plus a sub 1 times x to the first plus a sub 0. And this is where a sub n minus 1, right down the line, down to a sub 1, a sub 0 are real numbers. Okay, so I got a real number in front of each term. The domain of any polynomial function is all real numbers. Okay, and the degree is the largest power that appears. If f of x equals 0, then we say that f has no degree. Okay, and we'll look at that down there. Let's take a look at an example. F of x equals 3 times x cubed minus 8x to the fourth. Okay, suppose that we wanted to know if this is a polynomial. Well, there's two things that I'm looking for. Number one is that I must have a real number in front of each term, so nothing involving I, and every single power of x has to be a counting number. Okay, a whole number. X to the third minus x to the fourth, 3 and 4, those are whole numbers. And negative 8, 1, and 3, those are integers. And so this is a polynomial, degree 4 polynomial. Okay, the degree is just the highest power of x that I see. Okay. Suppose that g of x is equal to the square root of x. Okay. X to the 1/2 power is the same as the square root of x, so that's not a polynomial. A polynomial is where the degree has to be a whole number. Okay, n is a whole number, and 1/2 is not a whole number. Okay, h of x equals x squared minus 4 divided by x cubed plus 1. Okay, the top and the bottom factor, but no matter what we do with the factors, nothing's going to cancel, by the way. We're still going to be left with a fractional thing, so this is not a polynomial. In other words, we're not going to be able to get the function, the form that we need to be in this form here, because we're going to have a fraction to deal with. Not a polynomial. Okay, k of x equals 0. The power of x is 0, and 0 is in front of the x term. Okay, so this is a polynomial. Now this is the polynomial that has no, this is the only one that has no degree to it. And I'm going to comment on that a bit later. Let's take a look at f of x equals 8 first. Okay, so this is a polynomial. 8 times x to the 0. 0 is a whole number. Okay, a whole number, by the way, is just a number that's 0, 1, 2, 3, 4, 5. Okay, so I can't have like x to the 1/2. And then every single multiplier, a sub n, has to be a real number. Okay, 8's a real number. Okay, so this would be a polynomial. And this is a degree 0 polynomial. Now hold up. Why is this one a polynomial that has degree 0, and why is this one a polynomial that has no degree to it? Well, since x is equal to x times 0, which is 0, x cubed is equal to x cubed times 0, x to the 43rd equals x to the 43rd times 0. Okay, I can let the degree be anything, and I'll always have something that's false. Okay, so because I'll always have 0 coming out of that. So the 0 polynomial function is the only polynomial that we say has no degree to it. Okay, if f of x equals 0, we say f has no degree. Okay. Suppose that g of x is equal to negative 3x times x plus 2 squared. X plus 2 squared is the same as x squared plus 4x plus 4 times negative 3. Negative 3x times x squared is negative 3x cubed. 4x times negative 3x is negative 12x. This should be a negative 12x squared. Sorry about that. Okay, and negative 12 times 3x should be negative 12x. Okay, that's what we should get. So this is not a polynomial. This is a polynomial, excuse me, of degree 3. The degree is the largest power of x that we see, and negative 3, negative 12, and negative 12, those are real numbers. Okay, so both conditions are satisfied. 3, 2, and 1 are whole numbers. This is a degree 3 polynomial. How about h of x? And by the way, in the case of g of x, we're going to see that a lot, where we actually do have a polynomial that's in a factored form, and it may not look like a polynomial, but in fact it is a polynomial. Okay. Suppose that h of x is equal to the absolute value of x plus 2. Okay. Well, the absolute value of x plus 2. By the way, there's nothing involving absolute value bars here. Okay, so this is not a polynomial. But one reason to see that is because, well, first of all, there's no absolute value bars at all. Okay, but another thing is to see how the absolute value function is defined. The absolute value of x plus 2 is equal to x plus 2, and that's greater than or equal to 0 if x plus 2 is equal to 0, and it's equal to x plus 2 less than 0 if x plus 2 is less than 0. If x plus 2 is greater than or equal to 0, I should say. It's x plus 2 if x plus 2 is greater than 0, greater than or equal to 0, if x plus 2 is greater than or equal to 0, and negative x plus 2 if x plus 2 is less than 0. Okay, so that's one way to see why we have the absolute value bars. Not a polynomial. I don't have anything involving absolute value at all. So anything involving absolute value is not a polynomial. Okay. If f is a polynomial function of degree n, then f has n minus 1 turning points. Okay. So f of x equals 4x, or 6x to the 4th minus 3x squared plus 2x minus 5. First of all, this is a polynomial of degree 4. Okay. Since 6, -3, 2, and -5 are real numbers, and 4 is the highest power of x that we see. So what this says is that there's at most 3 turning points. Okay, now careful how we word that. Okay, at most 3 turning points means that we're not going to have any more than 3 turning points. Okay, there may be 3 turning points, there may be only 2 turning points, there may be 1 turning point. There's going to be none, because otherwise we'd have a line. Okay. Turning points are where we go from increasing to decreasing or decreasing to increasing. Okay. If we look at the end behavior of a function, now we don't know what happens in the middle, but suppose that that x is that n is greater than or equal to 2, and that's an even number, and a sub n is greater than 0. Okay, if a sub n is greater than 0, a sub n is a positive, and n is greater than or equal to 2, and that's an even number, like it is here, then we will always have a situation where the graph is going to open up on both sides. Now I have no idea how many turns are in the middle here. There could be at most 3 turns, there could be at most 2 turns. I don't know that, okay, because it depends. But I do know what the end behavior would look like. If n is greater than or equal to 2, and that's even, and a sub n is less than 0, okay, then I got a negative in front of the degree of the polynomial where the degree is some even number. And that's going to mean that I'll have a reflection about the x-axis, and therefore I'll have something that's going to be facing down on both ends. Okay, if n is greater than or equal to 3, and that's odd, and a sub n is greater than 0, and that's even. Think of like y equal x cubed, for example. Y equal x cubed is looks something like this. As long as n is equal to 3, or greater than or equal to 3, and that's an odd number, and a sub n is positive, then you will always open down on the left and up on the right. And I have no idea what happens here in the middle. Could go something like that, but I do know what the end behavior would look like. Okay, if n is greater than or equal to 3, and that's odd, and a sub n is less than 0, then transformations, I'd have a reflection about the x-axis, and I'd open up on the left and down on the right. Again, I have no idea what happens here in the middle. Okay, I could have a polynomial that's degree 5, and a negative number in front of that. Well, I know what happens on both ends. Okay, it opens up on the left and down on the right. I don't know what happens in the middle here. So that can be helpful information, the end behavior. When we stop right there, and we'll look at the rest of this in the next video.